We are going to be looking at another problem from the Leetcode Blind 75 list. So we are going to be looking at a graph theory problem. So the problem is titled clone graph. So first of all, we'll try to understand what the problem dictates, what is given as input, and what they expect as to be output. So let's just dive deep into the problem. So you'll be given a reference of a node in an unconnected directed graph, and you have to return a clone of the graph. So what you have been given is a structure node where you have been given two properties of that structure. The first of all is the value of that node, which is an integer, and you have been given the adjacency list of that node where the neighbors of the current node are contained. Okay, so let's see what details are provided for this problem. So since it's a graph theory problem, we need to know the properties of the graph. So the properties of the graph are it's an undirected graph and it's a connected graph. So it's a connected undirected graph. So that means that all the nodes are traversable from each other. So even if there is no direct edge from one node to another, we can traverse two nodes via an intermediary node. So we see that we can traverse from node 1 to node 3 by using 2 as an intermediate node or 4 as an intermediate node. When enough details of the problem have been understood, if you have been provided with these sort of problems in a real interview case, I think it's your job to find out all the relevant details of the problem by talking with the interviewer. So from an interviewer perspective, he or she would like it very much because that would pay for you to solve the difficult problem given the time constraint by extracting out the relevant details at the right time. So we see that Leetcode has provided a very useful visual representation of what should and shouldn't be returned. So we see that graph above, this shouldn't be returned because it's the same as the original graph. So and the graph below has different ordering of the nodes compared to the original graph. So you see that 3 is replaced by 2, 2 is replaced by 3. So the ordering of the nodes is different. So we have to return a graph which is sort of an exact replica of the original graph. Hence we can't reorder the nodes. Unlike case 3, in case 2, which is at the middle, there is no reordering of the nodes. The original adjacency list of each and every node is kept the same, and the blue circle instead of this yellow circle dictates that there is new instances created for each and every node. So new instances created for each and every node, the adjacency list is kept the same, the ordering of the nodes is kept the same. Hence we can return this answer as an acceptable answer for this problem, but we can't return the one at the top because we are not doing any sort of computation and we're just creating a copy of the original graph. So hence that cannot be returned, and neither can we change the ordering of the nodes and return it. Now that we understand what should be returned and what shouldn't be returned, we'll see how we can go about solving this problem. So if we use this case for illustrating our point, it's a graph traversal problem. Hence we can use the simple algorithms that we have learned for graph traversal, which is the first one is the breadth first search, and we'll also explore the depth first search. With breadth first search, if you guys remember, we explore all the nodes of the current node before jumping on to the neighbors of the neighboring nodes. So if we start at 1, we will explore the neighbors of 1 which are unvisited. We see that 2 and 4 are the neighbors of 1. Then we see that 2 is visited after 1. So now we'll go for visiting the unvisited neighbors of 2. We see 1 is visited, and the only remaining unvisited node is the 3, which is the neighbor of 2. We go to 4 now. We see that 1 and 3 are its neighbors. Both 1 and 3 are visited. We go to 3 now. 2 and 4 both are visited, which are the neighbors of 3. So the BFS would provide 1, 2, 4, 3. Unlike BFS, DFS would go in depth of the graph. So if we start at 2 and the next node that we explore is 2, then we'll explore all the neighbors of 2 now. So that's how it's different from BFS. So we go to 3, 1 is already visited, so all the neighboring nodes of 2 are visited now. And we see that next node is 3, so we visit the neighbors of 3. 4 is the only unvisited neighbor of 3, and 2 is already visited, and the neighbors of 4 are already visited, which are 1 and 3 respectively. You can also sort of do DFS in another way, because DFS doesn't have one straight correct answer. Depends how people choose to implement it. If you choose 4 as the next node to be explored, then you explore the unvisited neighbors of 4. So you go to 3, which is unvisited, 1 is already visited, and then you explore the unvisited neighbors of 3. There is 2, and then 4 is already visited, and 2 has 2 neighbors which are already visited. Okay, now that we know what BFS and DFS traversals are, so for the scope of this discussion, we'll sort of try to limit our discussions to BFS only. So for BFS, we need a queue to implement the breadth first search, to keep track of nodes that have been visited. And then for solving this problem, we also need a dictionary, so that we don't keep exploring the neighbors of the already visited node over and over again. Okay, so to implement breadth first search, so we'll first provide the current node to the queue. So we see that the current node 1 is inserted into the queue, and we'll keep running this while loop till our queue is not empty. So this one would represent our queue, and this one would represent our dictionary. Inserting this first element to the queue, if we pop it, and then we'll check whether this element is contained in the dictionary. If it is already contained, we'll not put it again. If it is not contained, since 1 is not contained in the dictionary, we'll insert 1 into the dictionary, and then we will explore the neighbors of 1. So we see the neighbors of 1, and there is an edge with 2 and an edge with node 4. So 2 is not contained in the dictionary, so we will insert 2 in the dictionary. And here is the more important part. So we started at 1, and we found out that 2 is a neighbor, and we saw that 2 is not contained in the dictionary. Whether 2 is contained or not contained in the dictionary, we have to populate the adjacency list of the current node which was there in the original graph. So in the original graph, 1 had a neighbor which was 2. We have to sort of make this connection here, and bear in mind this node 1 and this node 2 would be created as new instances of a node. So this wouldn't be the same node repeated here. Okay, so the next so when 2 is created as a neighbor of 1, we insert 2 into the queue. Now the next neighbor of 1 was 4, So we see that 4 is not contained in the dictionary. We'll put 4 here and then make a connection of 1 with 4 in our graph by creating 4 as a new instance of a node, new instance of the original node 4 in the original graph. And then we'll insert 4 into the queue. So all the neighbors of the popped out node 1 is explored. We'll move on to the next node in the queue, which is 2. We'll pop this from the queue and then try to explore the unvisited neighbors of 2. So we see that 3 is a node which is not contained in the dictionary, so we'll put 3 here and then we'll make a connection of 3 with 2. Okay, and then we'll insert 3 into our queue. Okay, then we'll find out that 2 has another neighbor of 1, but 1 is already contained in the dictionary, and also 2 has an we need to create an edge from 2 with 1. Since this is an undirected graph, we already created an edge with 2 with 1, hence we don't need to repeat it. So all the neighbors of 4 are visited. 4 was popped out. Now sorry, my mistake. So all the neighbors of 2 was visited. Now we'll pop out 4, and we see 4 is already contained in the dictionary. We'll not insert it. We'll go on to the neighbors of 4. We see that 3 is a neighbor of 4, and 3 is already contained in the dictionary, so we'll not insert 3 again. Now we'll make update the neighbor of 4 as 3 by creating an edge between them, and 3 was already inserted into the queue when 3 was a neighbor of 2. So all the neighbors and also just the same process. So 4 has a neighbor 1. The connection was already built since this is an undirected graph, so we don't need to repeat it. The last remaining element in the queue is 3, so we'll just pop it, and then we see 3 is already contained in the dictionary, and the neighbors of 3 are already in the dictionary. Both 4 and 2 are in the dictionary, and the connections are already created for 4 and 3 as the 4 and 2 as the neighbors of 3. Hence you see that we have reached the end of our while loop because our queue currently has become empty, and also in the process we have created a new instance of the original graph by keeping the order of the nodes the same as that of original graph, by updating the adjacency list of the original graph in the newly cloned graph, and by creating new instances of each and every node with that of original graph nodes. So all the constraints or all the conditions are met, and we have created a cloned graph. Now that we have finished our discussion in the drawing board, we'll just go towards solving this problem programmatically. We'll need to implement queue, so we have to import queue from the collections library. You see that in test case 3 we have been given a case where there is no node, so we have to keep track of this edge case. So if we don't have a node, then basically we have to return none. Okay, first we'll initialize our dictionary as an empty dictionary and a queue. We'll append the first node to the queue, and we'll, just like a BFS problem, we'll run the while loop as long as the queue is not empty. Now we'll pop an element from the queue if our newly popped element is not in the dictionary, we'll insert it by creating a key in the dictionary, and that key would be the new node. Here is what is interesting, and the value of this key would be the value of the new node. But we can't just assign the value of the new node as the value of this key, because if you remember, we have to create new instances of the original node. The way to do that is calling the constructor and passing this parameter in the new node value as the parameter to the node constructor. Now we will explore the neighbors of the new node. So let's just call the neighbors as nei. So all the neighbors you see that in the constructor itself, the list was called neighbors, which we also sort of talked about at the beginning of this discussion. So for neighbors in new node dot neighbors, if our neighbor is not contained in the node dictionary, we'll insert it, and the process is pretty simple. We just create a key like this, and then just like this, member.val, but obviously we have to create a new instance of the node object, and we don't want to be going into a case where our queue is empty but our neighbors are not inserted into the queue, right? So we need to append the neighbors to the queue, and whether those neighbors are present in the dictionary or not, if you remember the discussion from the whiteboard, we have to sort of update the adjacency list of the current new node. So the way to do that is we'll use the key with the new node and update the neighbors list of this key. So we'll append this neighboring node value to the neighbors list. Once we do that, we just have to return the dictionary of nodes, and that should satisfy all of our test cases. Let's see. Okay. Oh, sorry. So this should be node. Yes, so we have solved this problem. It takes a while because we are running a modified version of the BFS with the dictionary here, and the runtime complexity is just the same as that of BFS. So the time complexity would be big O of the vertices and the edges, because you see we are running BFS on the graph that was provided, and as long as elements are there and the connection between elements are there, we have to sort of keep running the BFS, and the space complexity would be the same, big O of V plus E, because we are creating a new cloned graph which is similar to the original graph. So both the time and space complexity would be the same with big O of V plus E. If you guys come up with solutions with even with less time complexity, you're most welcome to sort of provide that in the comment section. I would love to hear your feedbacks. Thank you, and I'll hope to catch you guys in the next one.